Hi, let's continue our lecture of memory. So last lecture we discussed why is memory so important and what is the confusion we are facing about different layers of memory, what is memory hierarchy, and why we have different types of memory hierarchy like cache, main memory, hard disk, and input of the servers, etc. And in a simple analogy we discussed why it is important and how it optimizes our latency. Okay, so this time we already discussed last time RAM and ROM, SRAM, DRAM, different names of terminology of volatile and non-volatile memory. Here we discuss the feedback, concept of feedback. Whenever there is a memory, there is a feedback. We should know there is a feedback everywhere. The feedback is the concept which helps memory to store or the computer to retain the value or data. Let's discuss what is RAM. So here we can see this is one inverter. I discussed what is the working of inverter. Inverter is inverting logic. If we have one input, inverter gives 0 as output. If we have 0 input, inverter gives 1 as output. So here this inverter is connected back to back here. So that means the output of first inverter is going to be input of second, and the output of the second is going to be input of second. So what is advantage here? Because of this feedback, even if we don't give the input for some time, this value is always reinforced. For example, if the input is 1, the output of the first inverter is 0, and this 0 is going to input of second inverter, and again it gives the output 1, and this 1 is reinforcing the input. So even if we don't have any input, this memory is reinforced. Okay, so this is the concept of memory. We have feedback, and here this is the simple understanding of memory, and this circuit is practically applied in everyday memory. Here this is RAM. This is RAM, random access memory, is designed using this back-to-back connected inverter. Okay, so this is the concept of memory. Now if we see the two additional transistor are adding, it's called access transistor. So what does it is used for accessing memory? Because and this is one, when this is kept high or activated, the connection to the input to the memory is inactivated. So that means when this transistor access transistor is high or it is on, I can now input the data, right? Same way we have the output transistors and the transistor output as well, which if it is make it on, I can connect the output of the memory into the bit line. So this is output transistor. This access transistor required for interfacing data to the reading into, so storing into the memory as well as reading from the memory. So it's inputting and outputting the data in the bit line. We need an access transistor. Okay, so WS stands for word line. Okay, the word line, activating word line, I'm activating the memory. All switches within the memory are designed using transistors, basically MOSFETs in modern technology. Now this is a simple 1-bit SRAM bit. So what is this? Have converted the inverter into a transistor level circuit. One is the PMOS. This is PMOS. The top level is a pull-up circuit, and bottom is NMOS, pull-down circuit. Okay, so basically these two transistors are required for one inverter. Now this is what the output of the first inverter is connected to the input of second inverter, and the output of the second inverter is going to output as well as it is going to the input of the first inverter. So this is called feedback. So we need 4 transistors for the 2 inverters which is connected in the SRAM bit. Okay, and if we add the access transistor also, it becomes 4 plus 2 6 transistors. Okay, so this is the 60 RAM cell. So we can see both inverters here. This is one first inverter here. This is first inverter. This is second inverter. Both are connected back to back. That means I'll just show you how the input of first is connected to output of second. Now the input of the first, say first inverter, for example, this is the first inverter. So the input is coming from the S line. The output of this is going to, the output this is going to the input of second. You can see that. Okay, and the output of the second transistor is coming from here, is again going to the input of the first transistor here. So basically this shorted, you can see this line is connected, sorry, this is line which is connecting here, input of the input to this here, and is connected to the output also. Okay, so this is back to back connection, we call M1 M2. Okay, so yeah, we'll continue this call. So we have 6 transistors. Okay, M1 to M6. Now how to connect this into a memory module? Okay, we have reading and writing a bit. So we have the 6, we already discussed this SRAM cell. This is the SRAM cell. We have the 2 inverters connected back to 2 access transistors. Okay, now this is connected to external line through a bit line. to a word line. Okay, this is a word line which gives the input to the access transistor, and this access transistor give a the memory connection to the bit line. Okay, once the bit line is made high or low are complementary. When bit line bar is 1, bit line is 0. That means they are complementary in nature, they are opposite in nature. When one bit line is 1, other bit line is 0, because this is their nature, because inverter outputs are opposite, we know. So we have a sense amplifier to sense which is 1. So we can, when reading a bit, it can be 1 or 0. Say for example we are reading 1 bit. What happens is, while reading 1 bit, we should not make the bit storage, because basically we are reading charge. So when we see the charge is high, we just need to check a small percentage of increase in voltage. We don't check the whole voltage, because if we make the whole bit 1 to drain, the charge will be drained and the bit 1 become bit 0. So to avoid that, we need a very good differential sense amplifier to sense the slight increase in the voltage. So slight increase in, say, one part of the bit line goes high, the other part of bit line goes down. That means you can easily sense that this part of bit line is high voltage, and this one is low voltage. So we don't need to drain the charge completely, and in less time we can sense that high voltage, and we can assume, we can infer that the charge storage is 1 or high. Okay, and the opposite for 0, it is opposite. When there is a low bit line is getting lower, we should know that bit line bar is getting high, we should know that is 1 is storage or 0 as corresponding to this. So we need a very strong differential sense amplifier. Now we will go to DRAM. What is DRAM? Dynamic RAM. What is the difference between SRAM and DRAM? In SRAM we know we need 6 transistors, but DRAM we need only 1 transistor. But here, because of dynamic, the word dynamic is used because D is D. Why D is used? Because we use a capacitor. Why the capacitor is used? Because capacitors can store charge. Okay, although for some time. Why? Because it will easily drained off easily. Okay, so because of this, we can charge store in a capacitor, and it has to be refreshed continuously. Okay, so it's called dynamic RAM. What advantage? We need only 2 transistors. Why 2 transistors? Because one is capacitor. Yes, modern transistors can act as capacitors also. So basically we need only 1 transistor, 1 capacitor, but in modern technology we can use 2 transistors. The capacitor itself can be designed using transistors. Here also we have a word line which uses connect to access transistor, okay, which connects to the capacitor, and a bit line. Bit line is the line where with the charge is released, and the voltage is increased or decreased, and this voltage in the bit line can be sensed using sense amplifier to infer the 1 or 0 bit is stored in the cell. And this is DRAM cell. We have the same thing, just inverted the diagram. This is DRAM cell. Now, because the advantage of DRAM cell is we only 2 transistors, we can have much more density, memory density than SRAM cell. That means DRAM, which we use it as our main memory in a smartphone or laptop. We call it main memory, 4 GB, 8 GB, etc. In smartphone also we have 2 GB, 4 GB RAM. So this is called DRAM cell. SRAM is basically used in the processor register, etc. But DRAM is used in the main memory. Okay. Now we have RAM, static RAM. We just compare. In static RAM, we need 6 transistors. Okay, first we all discuss, and retain value indefinitely as long as it is kept power. So although it's volatile memory, the power is required. We don't need to refresh it. That's it. Literally insensitive to disturbance such as noise. Because of its, it is always connected to VDD or ground. Charge is always preserved, and there is less chance of noise. Because it's always amplified. Back-to-back connecting. We should remember the back-to-back connecting inverter. That is SRAM. So it is less prone to noise, and it's more expensive and more faster. Okay, uses a cache and process register. Now DRAM, as we discussed, each charge stores each charge is stored in bits with a 2 transistor. Okay, one is capacitor and other is access transistor. And charge will refresh every 100 to 10 to 100 milliseconds. Why? Because capacitor can drain the charge, so it has to be refreshed. And it is sensitive to disturbance. Why? Because capacitor is always open to noises, because it is having less impedance in high frequency. So high frequency noises, it can disturb the capacitor. And cheaper, it is cheaper because the area memory density is much higher, so it's obviously cheaper. And okay, the same point. And use as all computers use as main memory. Now next time we use DRAM summary. So this is self-explanatory. Speed, you can see the access time. 1x for SRAM and DRAM is 10x. Okay, and it's persistent, right? And with less chance noises. and cost is also 10 times, 100 times than DRAM. Okay. Now we'll see what does a 1 bit cell look like. Okay, so when we specify memory bit, we should know there are two operations, that is read or write. Reading means we are accessing the memory bit and inferring whether it is 1 or 0, stored high or low, okay, etc. But writing to it, we are writing, we are storing something for permanent for future, permanently for future. So there is input bus, there are output bus, and there's a read-write bus. So this is called address bus, the data bus, and this is control bus. And select is also a data bus. We are selecting which lane of the memory or which row or column of the memory we are utilizing. So simplified RAM chip. So we already discussed, we need an address bus, we need a data bus, and we need a control bus, read write, and chip select, this select line. Okay, these two are the control part. Other thing are this is the data part, output, and input is the address part. Now this is self-explanatory. We have discussed there are two operations, write and read. Writing, we are putting data into the RAM, and reading, we are extracting data out of it, but it is non-destructible. Non-destructible means we are not destroying the charge store. Okay, that is already discussed, the use of sense amplifier, very good sense amplifier for the purpose. Now address and read. So now we have to know the RAM has n bytes, how many address lines are required. So we should know we have 100 lines in the RAM. So how many bits are required to access each one of the 100 lines, or 100,000? For example, each single line we can access 2 rows. For example, if the bit is 0, I can access first line. If the bit is 1, it is second line. Okay. So using only 1 bit, I have to select 2 different rows. So how many bits are required for representing 100 or 8? For example, we have 3 bits, we can represent one of the 8 bits. So 3 corresponds to 8 different rows or different places. Or for 100 places, how many we need? We need log 100 to the base 2. That means we'll get 6 point something. That means round cannot have a 6 point something bits, so we go to 7. So 2 raised to 7 is 128, which is greater than 100. So that is the only. So we have combined different memory blocks, and the number of bits in memory depends on how many bits it will fit. Okay, so this size of the memory depends on the storage. So if you have x bits, you have to divide into n rows and m columns. Okay, so this rest we'll discuss in the next lecture.